Okay, so the homework problems there that I picked was simply these. So that's one from chapter 3, one from chapter 4, one from chapter 5, one from chapter 6. I think they're relatively doable, and doing them will be good for you. It'll be a good review. So let me get this stuff out of the way. This window. Damn it, why can't I move the window? All right, now. Okay, does anyone have a question? I think it'd be good to deal with questions as usual. All right, if there's no question, let me review something from chapter 1. It's, first of all, inner products. Here, let's make this bigger so that people who are half asleep can see it, read it. Inner products are really important in geometry and in quantum mechanics. If you have the inner product is such that if you change the order of the vectors, you get the complex conjugate, and the thing is linear in the right vector, and it's anti-linear in the left vector. The inner product of a vector with itself is positive, and it's zero only if the vector itself is zero. So these are the standard Hermitian products called positive definite Hermitian products. And when we talk about quantum mechanics and most geometries, we normally, well, we often use these now. When I say geometries, in fact, the geometry of Minkowski space doesn't satisfy this because you can have a vector that's either time-like or space-like, and then depending on whether you choose a positive or a negative metric, the inner product of a vector with itself can be positive or negative. Anyway, one of the things that we learned followed from those inner products is that the inner product of a vector with itself is typically positive. You can take the square root, and that's called the norm. And if you take two vectors and normalize both of them, you can then compute their distance, and the distance will be somewhere between 0 and 2 if you just take the norm of that difference. On the other hand, there's another fancy distance called the Bohr distance, or the Bohr's distance, which is the arc cosine of the absolute value of the inner product, and that's between 0 and pi over 2. The reason why this Bohr's distance occurs is that the inner product of two vectors, when you divide by the norm of the two vectors, or the product of the norms of the two vectors, what you have is effectively a cosine. It's a complex cosine, but if you take the absolute value, then it's obviously a real cosine. And so that's one way of thinking of, you can think of an angle between vectors. Anyhow, one of the important conclusions from consequences of an inner product is the Schwartz inequality, and this holds for any Schwartz inner product. Remember, for Schwartz inner product, you don't quite need all of the, maybe I should flash back to that. So let me go back to inner products. for a Schwartz inner product, you only have that the inner product of a vector with itself is non-negative. You can't conclude that if the inner product of a vector with itself is zero, that it's actually the zero vector. Now let me jump to the Cauchy-Schwarz inequalities. And that's something that we went through last semester, or I should say earlier this year in the first few weeks, namely that the inner product of a vector with itself times the inner product of another vector with itself is greater than or equal to the inner product of the square of the inner product of the two vectors. Let me just write that in a somewhat different way. So let me say that it's the inner product of f with g, absolute value squared, is then less than or equal to the inner product of f with f times the inner product of g with g. And that has in particular over here a consequence. By the way, if we write this in Dirac notation, then it would look like this.
Dr. Cahill, your screen is hidden.
Oh, thank you. I keep doing that. And I'm glad that one of you tells me. That's really helpful. So that's the expression in Dirac notation. And what I want to jump to now is another consequence of inner products, a well-defined inner product. Not only do you have the Schwartz inequality, but you have something called the triangle inequality. And the triangle inequality basically says that here, let me see if I can do this on the board here. Let me say do it in blue here. If you have basically a vector here, f, and then you add to that another vector, g, that the sum of those two lengths is less than the length of f plus g.
Could you bring the board up for us?
What's that? In other words, the norm of f plus g is less than or equal to the norm of f plus. So here I need to.
Dr. Cahill, your board isn't showing.
Damn it, you're right, sorry. So it's less than or equal to the norm of f plus the norm of g. And that's something that is kind of evident just from geometry that, you know, if you need to go from home to the post office, you don't first go to FedEx and then go from FedEx to the post office. You just go directly to the post office. I thought I'd go through the proof of that because it provides a nice, it relies upon the Cauchy-Schwarz inequality. So what you do is you take this quantity here, this triangle inequality, and you take the square of it. And when you get the square of it, you get the absolute value squared of the norm is just the inner product of f plus g with itself. And by linearity, that is a sum of these inner products. The first one is the square of the norm of f. The last one is the square of the norm of g. And the ones in between are the inner product of f with g and of g with f. And these two things are these two things are obviously, this one is less than well, first of all, the sum of this plus this is a real number. Secondly, each of these is less than it in absolute value is less than or equal to its absolute value. And so if you add the two together, you get, if they're both real and positive, you just get that the sum of the two is twice the inner product of F with G. But if they're complex or if they're negative, then it's actually less than twice the absolute value of the inner product of F with G. But now the Schwartz inequality tells you that this is less than the product of the two norms. That is to say, the inner product of F with G is less than the norm of F times the norm of G. And of course, another way of thinking about that is that the inner product of F with G divided by the norm of F times the norm of G is less than or equal to 1, and of course it's greater than or equal to 0. And that's why you can think of this thing as sort of a cosine of an angle, theta, that's the angle between the vectors F and G, which are vectors in a Hilbert space of some kind.
Could you bring the board up for us, please?
Schwartz inequality to this line here, what we get is F.
Dr. Cahill, the whiteboard. Please.
Yeah, sorry. Yeah, what I was writing here was simply that the Schwartz inequality, in other words, this thing can be rewritten this way, and you can think of that as a cosine and of an angle between the two vectors in some abstract space. But anyway, getting back to the proof of the triangle inequality, what you do is you just use the apply the Schwartz inequality to this middle term. And then what you have is that the squared norm of F plus G is less than or equal to the norm of F plus the norm of G squared, each one squared, plus twice the product of the norm of F times the norm of G. But that, of course, is just the norm of F plus the norm of G squared. Now you take the square root of both sides and you get the triangle inequality. And if you let F be A minus C and G be C minus B, then the C's cancel in the first term and you get A minus B is less than or equal to A minus C plus C minus B. And that's another way of writing the triangle inequality. So I just thought I would do that as a review of chapter 1 because the homework that I assigned the extra in lieu of a final exam are not part of chapter 1. So let's see, we've got plenty of time. I don't know how long you guys want this class to last, but we can, if anybody wants to ask a question, do ask a question either in the chat box or just vocally. So make a suggestion or ask a question and I'll try to talk about either I'll try to answer the question or I'll try to talk about the topic that that you asked about. Remember, there are topics here that in the second half of the book, which I hope to cover in the course 467 next semester, if there are enough students. We need, I think, 5 or 6 students in order to teach that course. So if there are 5 or 6 students, then I'll go through many of these topics in the spring. But I could also talk about some of these topics right now if you'd like. What I might do, since nobody's asking a question or giving me any guidance, is just remind you of the singular value decomposition. This is the main theorem of linear algebra, and it tells you that you can write any rectangular matrix, which is to say any complex matrix whatsoever, doesn't need to be square. You can write it as a product of 2 unitary matrices and 1 matrix that's positive definite and non-zero only on its main diagonal. And of course, the main diagonal, let me switch now. The main diagonal here, if you have a matrix that looks like this, then the main diagonal goes along here and stops. And the value, this is called sigma. In other words, A is equal to U sigma V dagger. And the sigma is this thing that I'm talking about here. In other words, this sigma is this matrix here, which is in general rectangular, or it could be, well, it's always rectangular, sometimes square. And if it looks like that, then the non-zero entries are either on this diagonal or that diagonal if it's not square. If it's square, of course, they're directly on the main diagonal. U is unitary, V is unitary, and just by convention, one writes that as V dagger. And so that's the singular value decomposition. And in MATLAB, you can just type in SVD and bingo, it will give you the singular value decomposition. So let's see, do we have another, do we have a question here somewhere? I'm surprised that no one's asking me to do one of the homework problems. That's normally the fail-safe default question. Maybe I'll say a word about density operators. Normally when in textbook quantum mechanics, especially in the elementary courses on quantum mechanics, one emphasizes states and one talks about a wave function psi of x, and if one introduces Dirac notation, then you say that's the inner product of a position vector x with a state vector psi. And this is all well and good and true, but in actual real life, you rarely have a pure state. It's very hard to make a pure state. So what one often is dealing with is a density operator. And a density operator, the standard formula expression for it is rho, and one says that the density operator should be Hermitian. It should have a trace that's equal to 1, and the inner product of psi rho psi should always be greater than or equal to 0. In as much as rho is Hermitian, you can always write rho as you can always diagonalize it, and consequently, it would be, let us say, rho sub k, kk, so it would be a sum of outer products of the state vectors, k equals whatever it is, 1 to capital N, or it might be a continuum, it might be some sort of an integral dk of rho of k, k, k. And so the statement that the trace of rho is equal to 1 is just the statement that the trace of this sum of rho k, kk is 1, and this is just the sum of all the rho k's. And the statement that the trace is 1 is that the system, if you measure it, it's always found to be in one of these eigenstates, or at least the sum of the probabilities is unity, because the system must be found in some of the states. So there's a probability of, for example, 5% in state 1 and 15% in state 2 and so forth. And they all have to add up to 1. Steven Weinberg wrote a paper not that long ago in which he was suggesting that that in fact we should do quantum mechanics exclusively in terms of density operators. And of course, Weinberg being one of the very top physicists of our time, that's something we should think about. Of course, you might say, well, one particular density operator is just the outer product of a particular state, psi. For example, this would be the density operator in the case where you're talking about psi of x being x with psi and the system being in state psi. What Weinberg was thinking about, though, was putting some sort of a restriction on the density operators so that we weren't just talking about outer products of pure states. Anyway, I am looking for suggestions as to what to do, and I'm not getting anything in from the class. I could, let's see, does it, oh, gosh, I mean, the density operator in some ways is enormously physical, because it tells you it contains all the information we have about the system. And so it says, that it's composed of particles that are likely to have spin up half the time and spin down half the time, or spin in a particular direction 5% of the time and spins in other directions other percentages of the time. And it's, I mean, in physics, we've got the things that we write down on paper, they're all mathematical objects, and they all say things about physical objects. I don't know, that last question is almost more philosophical than mathematical or physical. And I was inoculated against philosophy and theology at a very early age. And so I'm reluctant to speak philosophically. I might jump to something here that's I wasn't thinking of talking about, but since nobody brings up a question, I'll just say something about Hamilton systems. If you have a Hamilton system of n degrees of freedom, you have n coordinates, n momenta, and their time derivatives are these partial derivatives of the Hamiltonian. And what you can then say is the time derivative of any object is the explicit time derivative plus something called the Poisson bracket, which is given by this expression here. And it was Dirac who realized that what people were doing in quantum mechanics was constructing things that were effectively commutators, and these commutators were analogous to Poisson brackets. And so what he did was say, well, that one could formulate quantum mechanics by saying that the commutator of A with B was equal to the Poisson bracket of A with B times H bar or IH bar, and so let me see if I've got that right, because I'm not copying from the screen, and so I'm not sure that I've got IH bar in the right place. The commutator of Q with P, of course, is just IH bar. And so what is the Poisson bracket of Q with P? Well, what we'd see here would be, it's the Poisson bracket of Q, that would be 1 times the Poisson bracket of P with P, that would be also 1, and minus 0 times 0, so this is equal to 1. So I did guess it right, namely that what Dirac said was that you could identify the commutator with IH bar times the Poisson bracket. Anyway, a Hamilton system with n symmetries has n conserved quantities, and if time translation invariance is one of the symmetries, and if the Hamiltonian and the conserved quantities are time independent, which means no explicit time dependence, then the system is said to be autonomous, and the Hamiltonian is one of the conserved quantities. And the Poisson brackets of the Hamiltonian with each of the conserved quantities vanishes. And in this case, we say that the conserved quantities have vanishing Poisson brackets and are in involution. That's the technical phrase. And an autonomous Hamilton system of degree n has n independent conserved quantities that are in involution. And that's then said to be Liouville integrable. And in principle, then one can integrate Hamilton's equations for these systems. This, of course, is something that isn't necessarily possible for an arbitrary Hamilton system. Here, I just thought I would show you some amusing things that one can do with MATLAB. The scripts are up there in GitHub somewhere in order, chaos, and fractals. And so these are the Q1, P1 coordinates of a harmonic oscillator coupled to another harmonic oscillator by a Hamiltonian, and I picked this Hamiltonian. This system turns out is not integrable. So two coupled harmonic oscillators display complicated behavior like that for equal masses but different frequencies. So if the frequencies are different, the system's not integrable. Here's another example, the two-body problem. Well, the two-body problem basically is integrable, and this is something that, of course, we teach in mechanics classes, two interacting particles moving in empty three-dimensional space. They're a system then of 6 degrees of freedom. The 6 degrees of freedom are classically a position and momentum for each of the, actually, no, I'm being silly here. Their position for each of the two, each of the two bodies. And, but you have 7 conserved quantities, namely the sum of the two momenta, the sum of the two angular momenta, and then the total energy. And the system's integrable, the motion is ordered, and if bounded, it lies on the surface of a 6 torus. Anyway, Hamilton systems are special. The time derivatives satisfy special identities, and the integral of P1 dq1 ... Pn dqn over a closed trajectory in phase space is a time-independent Poincare invariant. So that's one of the nice things about classical mechanics. And yeah, that's an example in chapter 14. Areas of phase space are constant in time along Hamilton trajectories, and that's and so that's true. But although Hamilton systems are special, few of them are actually integrable. For example, 3 interacting particles moving in empty space, and you might say, well, that's pretty damn simple. Well, it's a system of 9 degrees of freedom with only 7 independent conserved quantities, and it's called the 3-body problem, and it's actually, it's not integrable. I have not studied it. Many years ago, I talked with a physicist whose specialty was the 3-body problem, but I did not follow him into that field. Anyway, there are, you can have autonomous systems of ordinary differential equations. And what you have then is x1 dot is some function of the n coordinates, and then the time derivative of the nth coordinate is another function of the n coordinates. And even though this is restricted, it's actually by being of this form, it's actually more general than you can than it appears, because if you have a non-autonomous system of n equations, it's equivalent to an autonomous system of n+1 equations. You just set time equal to the nth plus first coordinate, and you write the derivative, the time derivative of the time is just unity, and so the n plus first equation is fn+1 of all of these is equal to 1. A system of n higher order ordinary differential equations is equivalent to an autonomous first order system of more than n first order ordinary differential equations. So here's an example called the van der Paul oscillator, and it has limit cycles. If you start it here, it'll spiral out and then sit on this perimeter. On the other hand, if you start it far out, it'll spiral in and then sit on the perimeter. So it's a limit cycle of that system. So different Hamilton systems can evolve in different ways, and if the system is dissipative, in other words, there's friction of some kind, then the phase space typically shrinks, and if it shrinks to a point or a set of points, those are called attractors. and an attractor needn't be actually a point or a discrete set of points. It can be a continuous set of points. And as in the van der Pol oscillator, where it was a perimeter, so it can be, or it can be a surface of arbitrary dimension, or it can be a fractal, which is a set whose dimension is not an integer. And if you have a fractal attractor, that's called a strange attractor. So this choice of adjective was a superb choice to attract attention to the field of Hamilton mechanics. The Lorenz system is a simple system of three first-order differential equations, and it has just a remarkable behavior. It starts out and then gives you this butterfly system which approaches a strange attractor. When early in the early 1900s, Henri Poincaré studied the three-body problem and found very complicated orbits. And what he found was that after a transient period, classical motion gets into one of four forms, either periodic, which is a limit cycle, steady or damped or stopped motion, quasi-periodic, meaning there are two or more frequencies, or chaotic motion. And chaos takes different forms in different dynamical systems. So there's no uniform definition of chaos. One definition is that two trajectories will diverge exponentially in time. So if you take, if they start out with a certain norm difference, then, by the way, I do not know why I have three vertical lines here. So let me ask myself that. Anyway, the distance between those points diverges exponentially. That lambda is called a Liapanov exponent. And one of the things Poincaré introduced was a map. And so if you have a trajectory in n-dimensional space, it can cross a particular surface, and on the surface, it will be the surface, of course, is of lower dimension than the whole space. And so you'll have successive crossings, which will look like that. And there'll be points on this space of lower dimension. So let's see, what do I want? I don't know how long we want to go on in this. The logistic map is one of the really important cases. The logistic map is something where you choose R somewhere, let us say between 0 and 4. Then to get to the point xj plus 1, if you're at xj, you multiply xj times 1 minus xj and then multiply all that by R. That is a model for a population with a limited food supply. And this, notice the thing is not invertible. You can't find xj from xj plus 1, because if you tried to, you'd get, it'd be a quadratic equation with two solutions. And what one has is basically chaos there. So if you plot xj as a function of R, and then see what the attractors are of this, or rather what the points xj are for, these are the last, these are 10 random starting points and the last 10 of the first 30,000 iterations of the logistic map, then according to what the value of R is, you get these points here. And they're points between 0 and 1, and there should be basically 100 points on each axis here. For each value of R, you'd have 100 examples. And you have this amusing behavior where you first have a straight line, not a straight line, a curved line, then a bifurcation, then a second bifurcation, and then multiple chaotic bifurcations. So but let me just, one thing, if you haven't, hold on, we've got a question here. Okay, so that's a complicated question there. I'm being asked, what could one do to distinguish between quasi-periodic and chaotic? Yeah, well, yeah, all right. I'd agree with you if you have something that's sufficiently quasi-periodic with a sufficient number of periods. I guess that would be hard to distinguish between a system that's quasi-periodic and actually chaotic. So I do not have an answer for you there. There is, by the way, somebody at Cornell, I forget the guy's name. I think I may mention him in things to read, do I? Let's see. Yeah, I think his name is Strogatz. You might want to, if you want to follow up on this, I would refer you to him or whoever that person is at Cornell that I was trying to think of. So shall I say something about fractals? This is a very simple idea, and the basic idea is that a fractal set has a dimension that's not an integer. And so the question is, how do you define dimension? And what are the plausible ways of defining dimension? If you want to see that, well, if I don't hear any objections, I'll do that right now. So Hausdorff and Besikovich introduced something called box counting dimension. So you've got some set and you cover it with line segments or squares or cubes, whatever you need, some sort of n-dimensional boxes of side epsilon. And in order to cover the set completely, you'll need n of epsilon boxes. These epsilon here is the size of the edge of the box. Let's say these boxes are always squares or cubes and so forth. So the edges are all of the same length, epsilon. And what you then take is the log of the number of boxes you need of size epsilon to cover the set, divided, and you take the log of that and you divide by the log of 1 over epsilon, and then you take the limit of that as epsilon goes to 0. That's called the box cutting dimension. Now, for example, if you have an interval a to b, you can choose n of epsilon to be b minus a over epsilon. And then you've just got, as you take the limit here, the denominator goes to infinity, and so this goes to 1. So that has ordinary dimension of an interval, which is dimension 1. On the other hand, if you take the Cantor set here, then you see you take a line and then you delete the middle third, and you do that successively. Then what you find is that you can cover the nth approximation with 2 to the n line segments, and each of them has length 1/3 And so when you compute this, you wind up with log of 2 divided by log of 3. And so the Cantor set has a dimension that's less than 1. It's not quite a line, but it's a lot more than a point, which would have dimension 0. Then another example is the Koch Snowflake, and which looks like this. You take a triangle, and then again, you replace the middle third of each edge with a triangle, and you continue in that way, and that's called a Koch Snowflake. If you work out that dimension, it's greater than 1, which is reasonable because this thing is becoming it's becoming more than just one-dimensional. Anyway, there are other dimensions of, one is the self-similar dimension. And then what you do is you count the number of self-similar structures of linear size X needed to cover the figure after n steps, and you take the limit as X goes to 0. So it's extremely close to the other one. I don't even understand why there's a difference. And then there are successive other definitions. And some of these were introduced just to make it easier to compute them. If you had an arbitrary set and you wanted to compute the Hausdorff dimension, for example, you might have a hard time. And so instead, Kaplan and York introduced something that's easier to compute. Okay, so that I think is plenty for for this particular topic. I don't remember what the Mandelbrot set is. I guess I did not include that there. I once heard a lecture by Mandelbrot, and by the way, I was sitting next to Roy Glauer during that lecture, and I asked him afterwards, I said to him, I think, or he said to me, and I think I said to him, wasn't all that impressed, or maybe it was he who said to me that he wasn't all that impressed with it, and I think Roy was right. So this chaos and fractal stuff had was hugely popular 20 or 30 years ago, and I think since then, I mean, it certainly has a certain amount of merit, but I don't encourage anyone to, well, go into whatever interests you. That's what I would say. So let's see. We have about a half hour left, or I don't know, if we actually go to the total length of the, I could go for a full 2 hours if you want me to. Why don't we jump to path integrals? Shall I do that? Path integrals are an application of quantum mechanics and some simple integral formulas, the Gaussian integral, in fact. So here are 2 Gaussian integral formulas, one with a purely imaginary exponent, and one with an exponent that's damped and imaginary. And there are these various generalizations of them. And there's also something called Trotter's product formula. And it's something that you'd certainly, any physicist would immediately agree to, namely that if you take something like e to the a over 3, e to the b over 3, e to the a over 3, e to the b over 3, e to the a over 3, e to the b over 3, then this is, as first approximation, it's just e to the a plus b, because there's no order in this formula, and to lowest order, it's obviously equal to e to the a plus b. And what Trotter did was to prove that as you take the limit n going to infinity, then this becomes exact. The path integrals are based on, well, quantum mechanics and statistical mechanics, but there are applications of this Trotter product formula, namely, if you take the momentum part of the Hamiltonian, you write the Hamiltonian as a momentum part and a position part or a potential part, in other words, kinetic energy and potential energy, or you just split it any way you want, whatever's convenient mathematically, then you can write the time evolution operator as a limit as n goes to infinity of n products like that. And so in physics terms, you say that e to the minus I big TH, which is the time evolution operator, you'd say that this is approximately e to the minus I epsilon h. Well, I'm sorry, I shouldn't have written h. What I meant to write was e to the minus I, that's epsilon. Oh God, I've messed that up, something awful. All right, hold on, let me just get rid of it. So this is e to the minus epsilon k, e to the minus I epsilon v, e to the minus I epsilon k, e to the minus I epsilon v, dot, 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 e to the minus I epsilon k, e to the minus I epsilon v. And here epsilon is equal to t over n, and you take the limit n going to infinity. And so this becomes an identity. This is for the time evolution operator. For the Boltzmann operator, you just have e to the minus beta k plus. Of course, here, what I should have said was, well, here, let me do it right. This isn't supposed to be h. This is supposed to be k plus v. And here, once again, it's e to the minus beta over n k, and e to the minus beta over n v, dot, 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 e to the minus beta over n k, e to the minus beta over n v. And you take the limit n going to infinity, and this is essentially an identity. Now you might say this is an infinite number of steps backwards from a solution to the problem. And in fact, that's the way progress is sometimes made. Instead of going in the direction that you've been going in, it's sometimes useful to turn around and go backwards and go around. What one arrives at is a path integral expression for the time evolution operator or the Boltzmann operator, and this path integral representation of the time evolution operator or of the Boltzmann operator, it's useful in some contexts and it's useless in other contexts. And so it's not a panacea. It's something that has some utility, and it's been very useful. And one of the remarkable things about Feynman is that he invented these path integrals in his PhD thesis many years ago. So long ago that I was a kid at the time. Anyhow, so what we do is we start out with complete sets of eigenstates of P and Q. And the identity operator then looks like this, but you can also write it as an integral over outer products of P states, and consequently, and the inner product of a P state with the Q state, of course, looks like this. And so what we're going to do is we're going to set the time interval, divide the time interval by little n, and write P squared, so I'm talking about one single particle here in a potential V, and just one dimension, and so I'm going to call P squared over 2m h bar, I'm going to call that little k, and V over h bar I'm going to call V, and then the time evolution operator is this, and I'm going to write it like that with the Trotter product formula. And then the trick then is you take the first pair of these and you take the inner product with Q states, eigenstates of position. And the reason why one writes it as KV is that you can, if you have Q states at both ends and you stick P eigenstates in the middle, then the P state is an eigenstate of the momentum operator, and the position state is an eigenstate of the position operator in the potential. And so this turns into e to the minus I epsilon P prime squared over 2m h bar, the inner product of Q1 with P prime, and then the inner product, and then e to the minus I epsilon V of QA divided by h bar times the inner product of P prime with QA. And you still have to integrate over P prime. But the integral over P prime is just a Gaussian. And if you use the formula that I said all this was based on, yes, beta is 1 over KT. So let me just write that down in red. Beta is 1 over KT. Thank you. I should have said that. I meant to say it and I just got distracted. So just use the integral formula and bingo, you get this. The dependence, by the way, of this matrix element upon Q1 is hidden, and it's hidden by the definition of QA dot. And that was up here. To carry these steps out, you set Q1 minus QA equal to epsilon times QA dot. And this is, if you want, you can call this a definition of what QA dot is. And the next thing is you just repeat this. So you've got your matrix element between QA and Q1. Now you go from Q1 to Q2. And so you write Q2, QA, and you put two of these things together. And when you do that, what you get is, you get this expression here. In fact, you get it almost immediately because you know what these are now, and you don't have to recompute them. And so you know this is just an integral over the complete set of states Q1, and you just have this. And now if you do this n times, what you find out is that the QB QA matrix element for a time period n epsilon is this expression, factor out in front. And by the way, you might say this is a really weird factor out in front. It is weird, but when you use path integrals, you're almost always talking about ratios of path integrals. So these factors out in front cancel. And what you wind up with is this thing repeated n times. And so you get a sum of these kinetic energy terms times I epsilon over h bar, and then minus a sum of the potential energy terms, and you integrate over all the coordinates, q1 through qn minus 1, that, and these are all the coordinates. So in other words, you're integrating over paths that, you're integrating over paths that might, let us say, start here, start here at QA and might go down here and then up there and then down there and then up there and then down, and till they finally get to QB. And so that's one trajectory, but then you also integrate over this one and so forth, and you integrate over all of them. And that's why it's called a path integral. It's integral over all paths. And now what is each path weighted by? It's weighted by this phase factor. And the phase factor, what you can see is that it's this kinetic energy minus the potential energy. Well, that's what we call the Lagrangian. And so the weighting factor is e to the I, the classical action of the process, divided by h bar. And what you do is you integrate that over all paths, and that's what is equal to the matrix element QB e to the minus I th over h bar QA. So that is the formula. And now, one of the things that must have delighted Feynman when he first figured this out. By the way, although Feynman invented path integrals, Dirac had something very much like path integrals, and it's hard. It's probably true that Dirac foreshadowed or foresaw many of the developments of theoretical physics and did not actually write them down and publish them, just as Fermi invented the Monte Carlo method without actually publishing it. He just told his friends at Los Alamos about it, and they used it in to make a weapon of mass destruction, and they then used it in more productive ways, or they published it and other people have used it in more productive ways. So one of the nice things about this is that you see, if you have some starting point here, QA, and you have some end point, let us say here, QB, what process is going to be the dominant process? Well, the process that will be dominant is the one such that this integral is biggest. And the integral will be biggest when the oscillations here from this thing and this thing, in particular, these oscillations are minimized. So in other words, if you have a path such that the neighboring paths have almost the same action. In other words, if the first order variation of the action is 0 along the path, then this is something that happens, and this is called a classical trajectory. On the other hand, if we consider some other trajectory here, and if you take adjacent paths, and instead of having the same action, they have very different actions, then these phases are going to wash out. And so the path integral tells you that classical mechanics and classical field theory, for that matter, is given by this formula, which is the principle of least action. One of my close friends, on hearing the principle of least action, this is someone who was not a physicist, but was at lunch, and we mentioned the principle of least action, and she turned to me and said, "That's you." Principle of least action. Well, anyway, however that may be, what you see is that classical physics follows from quantum mechanics because if the action varies along a given trajectory, that trajectory will not contribute substantially to the amplitude. So that's this statement here. So that's now if the action is quadratic, it turns out that well, let's see, this is sort of technical. I don't know if there's a real point in going through these things in detail. Well, all right, one application of the path integral is an understanding of what's called the Bohm-Aharonov effect. So there, what we're talking about is you have a cylinder with a magnetic field inside it, but it's a solenoid. So the magnetic field's inside it, it's pointing up, say, but the magnetic field out here, so in here, be not equal to 0, out here, be equal to 0. And now what Bohm and Aharonov predicted was that if you send charged particles past this thing, so you have a plane wave here of charged particles, what will happen is that you'll get some sort of an interference pattern on the other side. And in fact, that interferes. So in other words, the particles can go like this, or they can go like that, and so forth. And what is the action? Well, the action is given by this expression here, the kinetic energy, plus the vector potential dotted into the velocity times the electric charge. And q dot dt is just dq. And so this is an integral of 1/2 m q dot plus EA dotted into dq along each particular path. And this integral of A dq, the integral all the way around, so maybe I should switch to a different color. The integral of A dq around the solenoid is an integral of EA dot dq, and that is an integral of E curl of A dotted into the surface area enclosed in the loop. So it's dotted into this surface area here. And this is in fact an integral of E, of course, B dot ds. And so this is E times the flux. And of course, what actually counts here is the action over H bar. So we have a 1 over H bar here. And so what you expect then is to see fringes due to an angle like that, which is E phi over H bar. This would be the change in the action for two paths, one of which just went straight past the solenoid and one of which went around the solenoid. Now, of course, typically the paths don't go around the solenoid, but on the other hand, you can imagine a path that goes like this, and then another path that goes like that. And the difference between these two paths would be this path, and you go the opposite way to take the difference, and so it would be an integral around the solenoid, which is here. And these experiments were done and in fact observed this. This came to as a shock to many physicists at the time. This was probably 50 or 60, 70, 80 years ago. I don't remember when it was done. But the reason why it came as a shock to people was that the magnetic field out here is actually zero. And the idea that there could be a physical effect where there's no electric or magnetic field, that struck many people as being very surprising. But of course, the vector potential was not equal to zero out here. So A is not equal to zero here, but B is equal to zero and E is equal to zero. So let's see what is there something here about path integrals that I think maybe I've said enough about path integrals for the moment. So let's see, do we have any questions? And better yet, what about what would you like me to talk about or to explain? I mean, maybe something from earlier in the course. Maybe I could say a few things about AI. The basic thing that, or let me tell you a simple way of thinking about AI. It is not the normal way that people think about AI, at least as far as I know. AI people don't think about it this way, although probably some of them do. What you can think about is, let me just describe a particular example that I worked out in some detail. Reading handwritten numbers, and there's a website called Yan. yan.lecken.com, so forth. And there are 4 files that one can use to train and test a neural network. And then there are 60,000 images of handwritten numbers. And each one is a 28 by 28 matrix. So it's, in other words, you've got 28 pixels that way and 28 going this way. Sorry, 28. And so they're not super sharp images, but this was, there are 60,000 of them. And so in particular, each vector that, you know, describes, maybe this is a, these are handwritten numbers, so this might be 9 written this way, and so these pixels would be black and the other ones white and so forth. Anyway, each one can be thought of as a vector in a space of 28 squared, or 784 dimensions. And so one thing that I did, just to keep the thing, just to see if how well it would work, was I created an artificial intelligence solution, or a program that would read handwritten numbers based on this. And the idea was that if a particular letter I then represented, well, they are represented as these 28 by 28 images and vectors in 784 dimensional spaces, or in a space of this many dimensions, nearly 800 dimensions. And so what I said was, okay, let's, as take the training set and form an average vector of all the vectors in this space for the vector 0, and then maybe for the vector 1, the average of all the vectors is this, and for the vector 2, it might be there, and vector 3, it might be there, but these are vectors in a space of nearly 800 dimensions. And so then, in order to read unknown new images of handwritten integers, I just took that each of those images is then a vector in this space. And if the vector was closer to 1 than to any of the others, I called it a 1. If it was closer to 3, I called it a 3, and so forth. And that worked at an accuracy of 82%, and which isn't bad. What I think one can say is, well, it's obvious to me, and I think it's actually correct, namely that if these images were sharper, instead of being 28 by 28, if these were images in a vector space of, let us say, 10,000 or 100,000, or with a vector space with 1,000,000 dimensions, then, and if the resolution of the images that I was trying to identify were also vectors in 100, in other words, if it was 1,000 pixels by 1,000 pixels, which is what you get with an ordinary digital camera, or at least a decent digital camera, I think the accuracy would have been much higher. Now, is that the best way of analyzing handwriting? I don't know. Presumably there's yet a better way. In the neural network thing, you can read the description in chapter 17 if you want. And then you might say, well, what is this sounds really simple. What's the problem in doing AI? The real problem in doing AI is the data in. In other words, how do you make the training set? And so if you've got some collection of real world experiences, handwritten numbers or faces in a crowd, or, you know, shapes of plants growing in a field, images of insects. If you want to analyze those by artificial intelligence, what you need is you need lots of data, and you need the data, you need to somehow collect the data. And so it's the collection and the collation of the data, so that, for example, here, in this particular case, the data were images, 60,000 images of handwritten numbers, each of them 28 by 28 dimensional vectors, or they weren't written as vectors, but they were 784 values of between, I guess, 0 and 1. I don't remember where they were. But even here, there was an annoying and useless complication, namely they were high endian files. And high endian is a technical term for how the data was represented in binary. And most programs that we use are low endian these days. And so I had to write some sort of a program to translate high endian to low endian before I could actually get my program to work. But that's the least of it. The real problem is how do you collect the data? It has to be uniform in some way, and then you have to get it into a mathematical form, and there can't be any prejudice in taking the real world or physical object and translating your knowledge of that physical object into a mathematical representation of that object. That has to be done in a uniform way so you don't introduce biases. And then people who are pros in it don't do what I did, namely the simple matter of averaging things out. They create a neural network, and whether that's better and worse, I don't actually know. I imagine it must be better, but I'm not quite sure why. It's certainly much easier to do what I did than to create the neural network, but the neural network is not that much harder to do. And in fact, one of the amusing things is that it relies upon Moore-Penrose pseudo matrix, or is it the pseudo inverse? I think that's actually the pseudo inverse, not the pseudo matrix. It's a real matrix, not a pseudo matrix. So let's see, the class is certainly over. What about do you want me to go on? I can go on until 7:30 if you want me to. Okay, I think people are saying, yeah, that I've gone over time and you guys have other things to do. So I'm of the opinion then that the majority of the students would like me to end class now, but and so the best way to do this is for all of you to just leave the meeting, and when everybody's gone, I'll end the meeting. Let me just say one thing, though. This is a crazy time because of the pandemic and so forth. And also, we haven't had office hours for obvious reasons. We haven't had in-person office hours. And now, so the question is, and of course, the course is ending, but during semester break, some of you might have time on your hands and might have a mathematical or physical question that you would like to discuss with me. And so if so, send me an email. The best thing is to put 466 in the subject line so that I'll notice it. I get an awful lot of robo email, and so I'm willing to do that. I could even probably Zoom you and discuss at some point with you. And of course, obviously, it's good to ask me about things that that I know something about, such as the topics in the textbook that I wrote, or things in theoretical particle physics or things like that. Don't ask me about medieval history or how to pronounce Chinese words and so forth. Well, obviously that's what you do. You wouldn't ask me crazy questions. So I see there are still 12 people here. Of course, the fact is that these could simply be 12 screens on 12 computers that are not being watched by any human being in real time. So let me say this, that I'm going to end this class at 7 o'clock unless somebody says, please keep talking. And so you've got to, okay, if somebody says, yeah, I should say happy holidays to everybody. But if somebody on the chat thing says, please keep talking, I'll keep talking. Otherwise, I'm going to stop at 7. And remember, this virus is really bad, and it's airborne. And so the most dangerous thing is to be in a closed environment with other people. I see somebody's on Eastern time. Well, I hope you got there safely. I'm from the East Coast, actually. So let's see, I still haven't seen anybody. So let me also encourage all of you to sign up for 467 in the spring. As you know, there'll be, the main topics are those of this group theory and special general relativity, something about forms, more about probability and statistics, a little more about Monte Carlo methods, something more about AI, something more about order chaos fractals, functional derivatives. That's an important topic, and it's something that I found as a graduate student. I was never taught, and faculty members were constantly using it in their lectures. No one ever taught me, and I had to learn it myself. And in fact, my chapter on functionals and functional derivatives, I think, does explain it pretty clearly, and it's not that big a deal. But it's whether or not you take 467, if you're going to do theoretical physics, you really ought to read the chapter on chapter 19. There's also something on the renormalization group, which is some modern physics. And then I say a little bit about strings, but frankly, not much, because I've never actually written a paper on strings and I've never worked on strings. And also I find the title string kind of weird, because clearly if we're dealing with something physical, it's got to be of dimension greater than 1. All right, well, I haven't heard anybody say, please talk for another half hour, so I'm going to quit now and wish you all a Merry Christmas, a Happy New Year, and most importantly of all, a COVID-19 free existence. So I'm going to stop sharing and
Happy holidays. Thank you.
thank you. Take it
Thank you
easy.
very much.
Bye-bye. So I'm going to end it.